Okay, so yeah, today I will be talking about K-theory of inverse limits, in particular about K-theory of products. But let me maybe first just briefly recall the results from the previous lecture, which was the computation of K-theory of the K-theory of sheaves, because we will need this in the case of real line. So there was a theorem that if X is a locally compactable constant, and C dualizable K-theory. Well, I think I considered the case when it's completely generated, but this works for any dualizable K-theory. Then continued K-theory of the K-theory of sheaves and the values in C is given by sections with compact subgroup X with coefficients in continuous K-theory of C. And the same works for you can also consider non-constant presheaf of dualizable K-theories, and the same is also holds. And I explained like the kind of explicit computation of this in the case when X is a real line. So basically the special case is that continuous K-theory of sheaves on Rn C is just omega n, so it's sheaf by minus n of continuous K-theory of C. Let me also mention that like if X is a finite symmetric complex.
And this implies that K and
well, K0, you mean K0 of sheaves is Kn of sheaves.
Yes. So this looks like a way of finding yeah.
Yes.
Take K0 on the Rn.
Yes.
And it's not. How can you think about this? Who has a class of this? It's not objects.
Yeah. Well,
K0 is K1 of counters, and K1 is something more or less nested.
Well, not exactly, but you can still reduce it to K0 of some small category.
Okay. So Kn, so you are saying that Kn of C can be written as K0 of something which looks fantastic.
Yes, yeah. But okay, of course, it doesn't give you like effective way of computing K groups, but it just allows to reduce certain questions just to the case of K0. Yeah, and of course for negative K groups, we already everyone knows that just K0 of the iterated calculus was known.
Is there any map? Well, we have identification, but is there any map for which the simple map that would help
well, not exactly simple map, but yeah, I mean, sorry, here, you mean like it considers general situation. So I mean, it can be easily reduced to the case when X is compact, and then yeah, you can produce a natural map which then is an isomorphism. But okay, I would need to go into some details. Maybe we can discuss it later. Okay. For now, let me just mention that if X is a finite W complex, then we just see that so which is compact in particular. So continuous K-theory of the K-theory of sheaves is like maps from X to K-theory of continuous K-theory. yeah, this is kind of commutative invariant in X, but yeah, it's very finite, so it's never complicated. Okay, so the result for it, and yeah, and the result actually for the real line I will use to prove the following application. So like first goal for today. Yeah, eventually I'm going to talk about some complicated inverse limits in the dualizable world. But first, I want to formulate an application which is just about usual stable K series. So we will reprove the theorem. Yeah, for which that was approved by Kaspersky and Dinges. But I will give an alternative proof, which seems to be more conceptual. So that K-theory functor from stable infinity categories to spectra commutes with products, with infinite products. Yes, small stable infinity categories commutes with products. Yeah, with infinite products. Yeah, and the proof actually will use dualizable categories, and it turns out that the proof will follow from some abstract properties of the category dualizable categories. Quite surprising. Yeah, and the proof will involve actually taking products of dualizable categories inside the category of dualizable categories. So in particular, we'll we will see how limits work at least in the case of products. Then consider also more general limits.
Great. So you are saying that this is a non-trivial theorem.
Yes.
And now suppose what happens in a bit more? Suppose, for instance, is it true that okay, suppose you have an infinite product of equivalence? Is it true? Probably I will state I will make some wrong guesses, and but just is it true that K, for instance, K0 of product of infinite product of rings?
Product of rings, it's not true. I mean, there's a huge difference between taking product of rings and, for example, product of cases of fine projected modules of X and not round. If you do just K0 products of rings, it's really a same as
of course.
Yeah.
For instance, how to describe the function?
No, this will be a bunch of projected models, but of uniformly bounded rank, so to say.
Okay. So anyway, so it's not. And suppose okay, so it's important to work with categories.
Yes.
What if we work with additive categories of
Then this is true, and this was proved by Carlson, like more generally for exact categories. But yeah, what was for like exact one category, not infinity categories.
Suppose we have the notion of
yes, and actually for K0 additive categories, it's almost well, it's completely trivial actually that K0 or K0 commutes of additive categories.
And why and what about the
it's also true, but it's already requires a little bit of effort to see this for K-theory. Like you need certain criterion. I mean, a priori, you need, for example, when two objects have the same class of K-theory, a priori, you might need to use some number of relations in the definition of K-theory, and this number of relations which you're using might be not uniformly bound. But it turns out that there is a criterion of quality of objects K-theory, which works well in products. I will actually start.
So the short answer is that for its scopes, just for the
Yes.
scope,
Yeah.
statement for exact categories. It's true that was known for,
Yeah.
and it's true for the whole case spectrum.
Yes. Okay. Yeah.
And all of additive categories.
No, for K-theory it's open, but for
K-theory it's focused, but either for higher case or for additive categories. No.
Yeah. But here I will consider stable infinity categories, and I will explain how like there is a separate question about K0, but there will be after proving it for K0, I will explain how to prove it for all Kn using actually the theory of dualizable categories. Okay, so first there is a position due to Heller that well,
Is it Heller or Keller?
no, Heller. It's not very perfect. It's H. Yeah. So originally it was for exact categories, but the same proof just repeats for triangulated categories. So let's see triangulated category like small triangulated category, and we take two objects x and y in T. Then so the following are equivalent. Well, condition that class of x equals to the class of y in T0. Second is that there exist some objects z, u, v in T, and exact triangles x x sorry u x plus d v and u y plus z v. So there's very nice criterion of when two objects have the same class, and so basically, like one application is completely obvious, like that second applies the first, but that application is also not difficult. By basically using this condition two, you get defined equivalence relation on isomorphic class of objects. So basically, you can check that this is indeed equivalence relation. And it is additive equivalence relation, so you can model out, get monoid. It turns out to be a group, and you get alternative definition of K0, and then you just have two maps in opposite direction, which are inverse to each other. It's kind of a pleasant exercise to see that this criterion works. So corollary is that it's not so we don't even need stable infinity categories, just usual convex categories in Verdier semantics. We see that the natural map from T0 of the product of stable categories is isomorphic to the product of K0. defined cases. So I mean this map is clearly surjective, and for this case you just use this surjective. Okay, so that's a little effort which is required to prove the statement for K0. Now, the next observation, for which we don't need dualizable K-space at all, is just that we can deduce the result for negative K groups. So if another corollary of the experiment is that for a collection of stable infinity K-space, like small so for n negative Kn the product of Kn. And so the proof of this is it's actually not difficult. So basically we use the Calkin construction and so consider so we have the usual sort of sequences like Ci goes to incompletion, goes to Calkin K-theory, but I can just consider the product of this. So 0 goes to the product of Ci, goes to the product of countable incompletions of Ci. So the product of countable Calkin K-theories. And this is so this is a short left sequence. Okay, what I'm using here is that basically just the usual construction of the equivalence the commutes with products, which is I mean more generally just for the usual one case there is when you have order localization, some classes of model which satisfy, for example, right order condition, then localization compatible with products, just because you don't need any unbounded number of steps. Yeah, so this is a short exact sequence, and then to observe that the category is in the middle. It still has countable direct sums. So its K-theory vanishes. The whole K-theory. And then just apply induction on minus n. So I mean, for example, to prove the statement for k minus 1, so using this sort of sequence, it reduces to the statement about K0 of this product. Because we know which of K0 of this product, we use the commutation of k minus 1. So basically, it doesn't require any effort to deduce the statement for negative from K0. Okay, so now it's much more interesting to figure out what happens for K1, K2, and so on. And for this, so a priori, so I mean, naive idea is instead of embedding the case break into something with vanishing K-theory, you want to represent it as a quotient, something with a vanishing K-theory, and then proceed similarly. But it's impossible to do it in the framework of usual small stable K-theories. But it turns out that it's actually quite straightforward to do it in the dualizable. So now I will explain how this works. So basically, we'll prove the alternative. Let's call it theorem prime. Just alternative version of this theorem that continues K-theory from dualizable K-theory spectra commute with products. But now, of course, the products are taken in the case of dualizable categories, and they are quite different from the naive products. So, I will first explain just a little bit. I will give some general explanations about limits in the dualizable world. So, I mean, statement that limits in the case of dualizable categories exists, and second is not really a statement, but like a principle. They are very difficult in general, like very difficult to compute, to describe in general. So existence, yeah, there is a statement which I didn't prove, and maybe I will not lecture that this category is actually presentable, and so the existence of limits is automatic. But I will give somewhat sort of description of the limits, well, some way to describe them. Let's start just with the simplest kind of limits, which is the kernel.
So,
Yeah.
so you're not yet on the theorem, you are just explaining how to construct this limits for.
Yeah. Yeah. So I will. Yeah. I will. I will give some general construction of limits, which is not completely explicit, but then it will turn out that products behave much better than absolute. Yeah. So first, let's consider a very naive question. So what is dualizable kernel? So like kernel of a strongly continuous functor. So here C and D are dualizable. F strongly continuous. So this is just a fiber product of C and 0 over D. So this is kind of the simplest kind of limit. So the answer for that it is for this dualizable kernel F is the largest dualizable subcategory E inside the naive kernel of F, such that the inclusion functor from E to C is only continuous. This is not entirely explicit, and a priori it's not clear why this largest dualizable subcategory exists. But one can give a more precise characterization is that this dualizable kernel is so inside the subcategory of C, it is generated by objects of the form colimits of some functor phi from the partial set of rational numbers to the naive kernel of F, where for any a smaller than b, the map phi of a phi of b is compact map in C. It's not entirely explicit characterization, but it's and in practice this might be almost impossible to compute but it gives some kind of description. And yeah, so let me give just a simple example. Example, the dualizable kernel natural function from derived K-theory of ZT with derived K-theory of FT is 0. So, I mean, in this situation, the problem cannot be too difficult because there are only 4 utilizing subcategories of the derived K-theory of ZT. Just only 4 who complete subcategories. And you just need to pick the correct one. But here you see that the naive kernel is just Q vector spaces, but the inclusion is not strongly continuous, and the largest one, which is inclusion strongly continuous, is just 0. So in particular, we see that it's of course quite different. So the the functor from the dualizable categories, the presentable categories doesn't commute already this kernel. Yeah, and just another observation is that we see that corollary is that the dualizable kernels the dualizable kernel doesn't commute with sequential colimits. With sequential colimits. Well, simply because you can consider, for example, you can add all the power roots. So, like, we can consider the function from ZP adjoint the root power p to the n, the unit. Then, so the functor completes to the case of e, and the kernel is still 0. But when we pass to the limit over all n, so if we instead consider the kernel after passing to the colimit, which is the derived category of this infinite subatomic extension, then this is just the case of almost modulus. So this is the situation of almost mathematics. So this is derived case of almost modulus over this infinite totally ramified extension. So we see that kernels don't commute with already the sequential colimit. So yeah, the limits are not kind of badly behaved in general. Yeah. So now let me explain how general limits work. General limits. Well, there is a useful observation computing general limits. Let's consider this function from presentable categories. Oh, sorry, from dualizable categories. Well, unfortunately, there is no standard notation for this, but basically what I want to consider is not exactly the category of presentable categories, but the kind of countable version of it. So let's put omega 1 here. So this is category of omega 1 presentable categories. I mean, presentable omega-1 completely generated categories. And we allow only functors from C to D such that the right adjoint commutes. Okay, let's just say that the functors which take counter-represented objects to counter-represented objects. Equivalently, the right adjoint commutes with omega-1 fitted colimits. So can consider this version. Then, so if we denote this functor is f, let's say, proposition, sorry, proposition that phi has a right adjoint. Which sends C to the incompletion of counter-represented objects in C.
Can I interrupt you? What's the difference between those lines, the left and sides?
Sorry,
There's the infinity.
sorry, infinity. Yeah, I expect all the power rules.
And the colimit there is in TRL.
Yeah, but it is the same as colimit in the dualizable case. Yeah. And actually, the fact that it is the same follows from the fact that there is a right adjoint. So this right adjoint sends this presentable category, but with this condition being omega-1 completely generated, it sends it to incompletion of counter-represented objects. Yeah, and okay, let me just comment on the non-trivial part of this adjunction statement. So I mean, if you have so if you have some map from so take C dualizable and D presentable omega-1 completely generated, and so if you C to D, the functor from C to D, like in this category, such that which satisfies the condition f of C omega-1 contains D omega-1. Then this functor under this adjunction, it corresponds to the functor which is the composition. So C goes to, by using phi hat, goes to incompletion of C omega-1. And then you just apply input of f go to input D omega-1. Yeah, so this is how this adjunction works in the non-trivial direction. So having a functor, a presentable category with this condition, multiple objects, you get a functor from which you get a strongly continuous functor from C to incompletion of this counter-presentable.
So what?
I'm making a comment on how the adjunction works.
But and let's find the junction.
I'm doing slightly different thing. I'm just taking an object of the first category and object of the second category, and yes, yeah. I mean, yeah, of course, it can be done just by constructing unit per unit, but it's instructive to understand how they respond. Let's just to make it less confusing, let's write it phi of C, but phi is just phi of C is just the same category, but consider this represent. Okay, so this is how it works, and now yeah, now this gives actually a way of this gives some sort of description of limits in dualizable categories. Rule is that for functor, let's say from some category I to dualizable categories, I goes to Ci, the limit let's just write limit dual, meaning that take limits in the category dualizable categories Ci is the following. So take the dualizable kernel function from the incompletion of the usual limit of categories of counter-represented objects to the incompletion of the limit of this Clausen continuous Clausen categories. Yeah, which looks kind of scary. So and in general, it's full generality. It's not really vector computed, but it exists. Yeah, but what we will be interested in is actually situations where this limit is very well behaved. The situation will include the case of formal schemes. For systems of categories coming from formal schemes. Yeah, and it will certainly include products. So now I want to specialize to the case of products. Okay, so but before continuing with this discussion, it's useful to just give one more characterization of dualizable categories, because this way of thinking will be useful later on. So just proposition, and I think this observation was made by Clausen and Scholze. At least I didn't even think about this point of view before reading the notes. Is that for representable category, following are equivalence. First, that C dualizable. Second, that the prototype's axiom 86 holds in C. And so just to recall what this means. So for any directed partial sets, GI. So for any family of directed partial sets, and for any functors from GI to D, so that's GI small goes to some X GI. We have an equivalence. So we can take product over I of colimits over this direct facet of XGI, and we have a natural map from the colimit over the product of this direct facet of products over I of XGI. So it's kind of and this has to be an equivalent. I mean, this axiom 86 it's contained in this Tohoku paper of prototype, but I think almost everyone either ignored it or forgot about it. So I mean, I think almost no one knows that this axiom exists. But recently it turned out that it's very relevant. Actually, this theory of dualizable categories. Yeah, and okay, so I need to make some remarks because for people who are unfamiliar, it might look quite confusing. Remark is that A6 is originally for inner category, but it makes sense for any category with infinite products and filtered colimits, of course. So I mean the formulation makes sense. And just remark the fact of life that A6 holds in the category of sets, which is just the only thing which you really check just by comparing the elements of the set, and then it follows automatically that it also holds in the category of groups, in the category of spaces, category of spectra, and in any computer generated in the category. And in fact, in any computer assemble category. Not even necessarily stable. What representable category. Okay, but basically, like after you know that it holds for sets, for spaces and so on, what this actually means, like equivalent way of formulating this, is that colimit functor from incompletion of C to C commutes with infinite products. And okay, up to theoretic issues, commutation of the functor with products is equivalent to the existence of left adjoint in the case of stable large categories. So at least like one direction is clear. So if the left adjoint exists, so the category is dualizable, then this colimit functor has to commute with products, and this can be rewritten in terms of the axiom ABC. Yeah. So yeah. So and we will actually use
What was the statement? Two is equivalent to.
I mean
So is this three or three, which is the core?
let's put this in brackets. I mean I mean after you know in for categories of spectrum, for example, you see that this condition just states that the colimit functor from incompletion to C commutes with products. Yeah.
It's impossible for me to follow the details. I want to understand the thing. So the statement here is, if you the statement is that dualizability is equivalent to x6, and then x up6 is equivalent to the property from NC to C. And then I'd like to explain why. I didn't quite understand why, because the speed is big. But I want to be sure that I can write down the correct statement. So the correct statement is that 1 and 2 is equivalent to this third. So maybe a general quest is to formulate statements before explaining why.
Okay. Yeah. Yeah. Okay. So this is crystallization of dualizable K-theory, but we will actually use repeatedly just the fact that EB6 holds in the K-theory of spectrum. So now, like after I recalled what EB6 is, can actually say something about this products in the infinite products in the K-theory of dualizable K-theories. So let's first make one observation, which might sound confusing, like for people who didn't think about this. So observation position. Consider some small categories, let's say AI, small segment categories. And consider some int objects and I, and also an I which are int objects of opposite categories. Then we have like product of mi considered as an int object of the product of ai, and product of mi considered as int object of ai opposite. Here, let's say that I am identifying this category with functors, exact functors from product of AI opposite spectra. And similarly here, functors from product of AI to spectra. And when I say the product, I'm just literally taking the product of the corresponding functors from AI object.
So in other words, you have when you write the product is belongs to something, it's a statement, not.
No, it's not yet a formulation of the proposed. I didn't finish the formulation.
Okay, but yeah, but the first claim is that when you write product, consider the product as sets of functors,
Yeah.
then there are what indirects.
No, yeah, it's not even. I wouldn't say that there is any non-trivial statement here. I'm just considering. I am treating each mi as a functor from AI opposite to spectra, and then.
So the claim is this product, but maybe the claim is easy, but
Yeah.
there's still a claim that the product is in.
Yes. But now the statement, which actually requires a little bit of thought, but actually follows from EB6, is that when we want to take the tensor product of mi, like we can take the tensor product of int object of some category over this category with the int object of the opposite category. This is actually also the co-evaluation, evaluation in the terms of this, terms of dualizable objects, dualizable categories. So this is the evaluation, and the statement is that this is the same thing as the product over I of mi tensor with ni over ai. So, like, if you do the same thing instead of categories, if you just consider rings and right modules and left modules, then the analogous statement wouldn't be true at all. But it is true if you consider, like, roughly speaking, like modules over categories. And this case, this taking product of right modules, product of left modules, taking that as a product over the product of categories, this is the same thing as first take the products and take the products. So I mean, it's really just, I mean, just a formal exercise. What are there questions at least about formulation of this?
Okay.
Yeah.
So M sub I, if M sub I is living in indivisible, is the product of M sub I, and I think of that as literally the product of like each M sub I is embedded sort of diagonally in the end of the product, so zero and all the other terms.
If you think about it as a functor, or you mean in which way?
Sorry, I'm saying, so M sub I is an indivisible.
Yeah.
Well, end of A sub I embeds an end of the product, right?
End of
End of A sub I embeds an end of the product.
yes, but it's not what I'm doing.
That's not what you're
I mean, what I'm doing is considering it like this, as I'm considering the product of Mi like as a function from the product of AI opposite to spectrum. I mean, each Mi gives a function from AI opposite to spectrum, and I can just take the product.
So it's not a product in the input. It's not a product inside an input.
Yeah, it's not what you said previously.
Oh,
Yeah, but yeah, what I'm trying to say is that just applying 86, you can see that you get this a little bit surprising computation of product with tensor products, which looks a little bit counterintuitive, but still works.
just so it's 86 was a property of
Yeah, but in particular it's called for spectrum.
it's called for spectrum.
Yeah.
And here you apply X6 for
For
spectrum.
spectrum. Yeah, just yeah. So apply 86 for spectrum.
This between those two long lines, those short expressions.
Sorry, this. And just a comment that in completion of the product, it has the same as functors from the opposite category perspective. I mean, exact functors. It's just general completion of any small category, mostly open category. Okay, so now using this observation, let me explain how products work in dualizable categories. So let's keep this. So the proposition is that just that the functor from small category to the dualizable category commute with products. So for a collection of small stable infinity categories, so the natural math, the natural function from incompletion of the product AI is equivalent to the dualizable product of incompletions. Just a small stable infinity categories which are currently complete. So perf intuitively means that they're like perfect modules of the sum. Yes. So this is like third statement, and the second statement is that for general dualizable categories, the function from the usual product of one compact objects to the usual product of counting categories, continuous counting categories, countable ones, is a homological morphism. Which implies that this dualizable product of CI is just the usual naive kernel of the function from the incompletion of product of non-represented objects to the incompletion of the product of countable Calkin categories, continuous countable Calkin categories. Yeah, so in other words, in this case, the limit, which is the product, is extremely well behaved. So we when we take this dualizable kernel, we actually don't need to do anything. We just take the usual kernel. Yeah. So okay. Actually, the first statement. For the first statement, we don't even need this proposition. H. For the first statement, we just observe that the product over I of this short exact sequences 0 to I to countable completion to countable Calkin category. So when we take the product, this is still a short exact sequence, which we already used before, but just because reject motions commute with infinite products, and periodic completions also commute with infinite products. So the first statement doesn't even use AB6 at all, and the second statement is just basically, roughly speaking, we just need to apply the proposition about tensor products. Proposition above is on the right node. So yeah, and later we will need a much more complicated statement that about that the limits are well behaved in the case of formal schemes. But this is in this case this is really easy to understand. I mean, the only effort which you need to make is to understand this statement about taking tensor product. This non-standard situation. Yeah. Sorry, recall what is just a comment. Yeah, homological morphism is the function between small categories. The homological epimorphism if its incompletion is a localization, or in other words, if it's a Gaussian function.
One more the population. So the functor from NP to
Yes. Yeah.
That's a right adjoint, which
Yeah.
and then
It has to be qualified.
consider question and it is a order and
Must be identical.
yes, and in which order?
First refix scalars, then accent.
So if you go first from NP
Yeah.
by restriction,
Yeah.
and then from NP by
Extension, yeah,
introduction.
Yes. And this translates into statement about tensor product of right right A module and the left A module, and basically what you do is you just compute this tensor product using this general observation. That's how this works. Okay, just remark. Can generalize this second statement is that for any homological homomorphism, for any collection of homological homomorphisms AI to BI, for some index set, the product of this homological homomorphisms is also homological homomorphism. So basically, yeah, this is just application of the axiom AB6, which holds for spectra. Yes. I mean, which is equivalent to the statement that it holds for abelian groups. Yeah, right now. Yeah, let's actually make okay. Well, let me just formulate a corollary, immediate corollary of this. Yeah, which is just yeah. Okay, the corollary is that corollary is that just two statements about commutation of K-theory with products are essentially equivalent to each other. So so okay, let's put it like this: that K-theory, like the statement that K-theory, the usual K-theory commutes with products. Only continuous K-theory commutes with products.
Yes, so our goal is to create.
Well, the first statement,
You went through the first
Yeah,
statement
yeah.
and was in it's not the second statement.
yeah, but
And so the two statements are equivalent and seem to say they are correct.
yes, yes,
We have it here.
yes,
So now we have it.
yes. Yeah. Okay. So the second part, I will try to be maybe less technical, but at least I have explained the main statement holds here, and like for example, what is the general idea of so how do we actually prove this limitation with products, like using this idea of taking shifts on the real line. So
Can I ask for so just about the proposition?
yeah.
Tell me more about the different part. I think I didn't understand how you the idea.
No, I mean, I give the instruction how to compute the general limit plausible case series.
You mean on the board in the middle?
Yeah, yeah. And basically what we need to do in that case, we would need we need to take the like take incompletion of this product and incompletion of this product, and then take the dualizable kernel of this function. But the dualizable kernel happens to be just the actual kernel, and the actual kernel is incompletion of the product of AI.
It's part one, corollary of part two, is that the idea?
No, part one is just corollary of the general utilization of dualizable cases. Sorry, general position of limits in plausible categories. And just the fact that the product of Verdier quotient is a Verdier quotient. Verdier quotient computes this product. So it is part one using only that. And part two using this more tricky computations with tensor products of infinite products. Okay. So now let me.
The result of all this consideration is the problem to proving that K-cont commutes
with products, yes. Yeah. Now let me formulate, but like without going into details. So just the abstract properties of the case of dualizable cases, which I will need. So first, in the case of presentable case, there is infinite product over some index set of short exact sequences. But I mean, product in this dualizable world is still a short exact sequence. Just like in the case of small cases, which we already used. So, I mean, this requires a little trick, but still it's some kind of formal manipulation. So it's not kind of so complicated. Basically, it uses the same ideas. And second, which is less trivial to understand, is that just the axiom E6 itself holds in the case of dualizable cases. So as I said, AB6 is the statement of AB6 makes sense in any case there is infinite products and trivial continuous. In particular, it makes sense in this case. So I'm just saying that it holds. And this can be checked using the statements which I mentioned. But that will not go into details. But now, just using this knowledge, I will explain how to use the computation of K-theory with products. Basically, I will explain how to prove the statement for all K groups, starting from the statement about K0. So, actually, we already know that K minus 1 continues from dualizable categories from conventional products. So
why do you know that? From the set. Yes.
from dualizable, yeah, dualizable.
From dualizable.
Yeah.
Why?
Because it reduces to K0 of small using. So what we want is assuming the result for Kn continuous deduce it for Kn plus 1. Like previously, what we did without any effort is that for usual K-theory, we assume, like, if we know it for Kn, we deduce it for Kn minus 1. So that's, it was just trivial application of the Kalkin construction. But here it's much more interesting. The idea is the following. So recall that yesterday I considered this K-theory of shifts with non-negative singular support. So recall K-theory. Let's just call it shifts non-negative are values in some dualizable category C. So shifts with non-negative. Single support is contained in the non-negative part of the potential bundle. And then we have the statement that that it's continuous K-theory that actually vanishes. But now can observe that there is a natural motion counter from this category to C, which is just section support. Observe have short the sequence like following the notation of Schwaber and Shapira book. Okay, some modification of that notation. So we have the sections with complex support counter to C, and this is a evolution counter, which is easy to see. Right, adjoint upper tree counter, which is not the point, commutes direct sum, and we have a kernel. Like in the Schwaber and Shapira book, it would be denoted as like shifts on R, C, this R positive. Let's just use this notation, shifts, which are like supported, single support is strictly positive. So we have this short degree sequence, and in fact we only need to prove that if we consider infinite collection of dualizable categories, then continuous K-theory of the product, dualizable product of this shift with non-negative support is zero. Because after that we will be able to obtain this inductive process, because so the statement about Kn plus 1 for the product of Ci would follow from the statement about Kn for the product of this case. So we just go in the opposite direction. But we still need to prove that continuous K-theory of the product of this categories of dimension theory still has zero K-theory, which is not yet clear because we don't yet know the commutation.
What answer you have many of?
Oh, sorry, yes, we have some here. Yeah, sorry, we have some categories here. Take product. Yeah. So now this actually follows from the fact that 86 holds in the case for dualizable categories. So let me just briefly explain how this works. Okay, so so we have this this sequence which already appeared yesterday. So we have this. Okay, so for each individual CI, we have the following. So we have shifts with no negative single support, where the CI goes into functors from whole set of real numbers, contravariant functors, right? And this goes to the product, but the usual product of copies of CI over all real numbers. But now, because the dualizable products are of short exact sequences are not exact, we can just take the dualizable products here for I. So we just need to see that K-theory of this is the same as K-theory of this. But now this is just both things can be written as certain crazy colimits. So let me just briefly sketch. So if you're interested in continuous K-theory of this, then basically using EB6, just in using the commutation of continuous K-theory with colimits, fixed colimits, we see that this is the same as colimits over all families of finite subsets of the real line. Maybe of unbounded cardinality, but each of them is finite. Of functors of just reputation of the Dinh-Quiver, just there's this subset Si, considered as a partial ordered set with the opposite order to CI. Sorry. Continuous K-theory of the product. Okay. And if we do it for the right hand side, we're getting essentially the same thing. Over the same directed partial ordered set. Continuous K-theory, the product of I, yeah, the right hand side. Of just finite product of corpus of CI over SI. We have an initial map here, but now it's just now it's easy to conclude. So colimit over families finite subset of the real line. Okay. To conclude, we just need to observe that. So for each particular I, it's just we have just equivalence between representations of the Dinh-Quiver and just the direct sum of corpus of like K-theory of representation of the Dinh-Quiver and direct sum of K-theory of corpus over the values. But now, conclude, we just need to observe that like dualizable product of some K equivalences is again K equivalence, where by the verbs equivalence I mean a very straightforward thing. So a functor from C to D, in the logical case there is K equivalence. If there exists a functor in the opposite direction, both only continuous, such that both compositions are have the same classes as identity in K0 of n function. So just equivalent is the very nice. Zero of continuous, only continuous on the functions. And similar for that. So that's basically the idea of how to prove. Basically, the idea of how reduce the questions for higher K-theory to K-theory. So if you just use the fact all shifts on the real line and combine this with the axiom AB6. It likes application of dualism. The rest is just writing down all
the class of G is the class of identity in K0 for.
Oh, the strongly continuous and the functors of the H grid. String font, yeah.
There is this extra line shift support K. Why? It's assumption absolutely has nothing to do. So what is the goal of this? Auxiliary part.
I mean, this is sort of a natural construction of a K-theory whose K-theory vanishes for some
Which
projects to the there. Yeah. So it's like the opposite to the usual inclusion completion, but now. And we couldn't do it in the world of small games. Well, at least no one knows. Yeah, but yeah. No, I mean, okay, you can do some tricks like whenever you have dualizable categories, you can pass to small categories by taking out construction, but it's not the most measures. Right? Initially obtaining the original category is can be done in dualizable.
That this that keep on the real line that you can sort of witness the fact that they're either to the zero and some very fine
You mean the classic motive is zero?
Yes.
Yes, but the proof is just the same as the proof which I gave for K-theory. Because it's just universal. I mean, I only use the K-theory as classic variant and commutes with colimits. Same applies to the universal.
So what are you said that sort of in the association. It's a sort of nature of the
Yes.
of your
Yes.
of your data.
Yes.
How in construction so
Yeah.
and that actually sounds dualizable completely generated.
Yes.
But here you have a wonderful deal. And the question, so and suppose that I have just stupid question. Suppose that I have a dualizable category, yes, then I can consider calculate which would be what completely generated.
Yes.
And suppose that I go back using your construction with this auxiliary element. Do I get my category back?
No, you get something much view, but with the same. And you can also do another. Yeah. Okay. Yeah.
If you do calculate and then we shift it.
Yeah. Yeah, this you can do for any dualizable category. On the other hand, you can start with completion with a small category and you'll take this shift, like with positives, then take out construction and get another small category. It's in K-theory, but just much deeper. Yeah. But I mean, this question, I mean, the original question, computation with K-theory with products, I mean, it seems to be really, like really difficult. Like there is no completely simple proof. What we mentioned in words, there is another open question, a closely related one about interspaces or get commutative monoids in the pure spaces. So there is an operation of group completion, just adding elements, and no one knows if this can use with infinite products. And there, for some reason, this happens to be the case for infinity spaces, which come as spaces of objects. This is true, but there is no like completely elementary proof of this.
But it actually is true.
But for arbitrary, yes. Well, no one knows. I mean,
And if you consider something that's clear, then simply.
no, then it's just the usual group completion of conventional noise. Then it's kind of formless. But then again, there is
Products, actually.
no. I mean, you just consider formal differences. Okay, so that was the discussion. It's almost. Oh, yeah.
My plans for it takes technical.
Yeah, but still, my plans were as usual too ambitious. But now, after we know the statement about products, I wanted to actually start explaining what happens with formal schemes, like what kind of K-theory is shaped with the formal scheme. And this will be actually a more complicated limit, which is sequential understanding. And for today, let me not go into into the. I will not have time to go into details of the proof of commutation of K-theory with the but at least I will give you three different characterizations of the same category. Three different points of view of how you can obtain the same category. Why is it better than the naive category? Okay. That's kind of the main. Okay, yeah, but
So, I mean, this fact that K-theory because of different products of stable categories. Like it's a statement that, like in the form of active K-theory, it just uses like the K-theory additive.
Yeah, the only thing which I used is that my proof shows that if you take any locality invariant which commutes with the fitted colimits and such that pi zero commutes with products, then it commutes with products. I mean, the invariant is very suspect. So that's the only thing I used. So first I explained the proof for K0 and then just using that use for all K proofs.
I guess that's my answer to that. Do you think that using applying directions to realize what kind of places is really is essential for the full statement seems to be at the level of that.
No, it's essential. Well, at least it's essential for this approach. Yeah.
Such, but you can pass your developing twice.
Yeah.
You can do it.
Yeah.
Then you pass. Then you have to loop the count.
Yeah.
And then the thing would be generate
Yeah, but that's certainly true. But I mean, you want to work with something you can control, okay, this construction in general, which uses like dualizable case comprehensive with up to shift by one. But now since we can do shift in both directions, yeah, you're right. We can every time we can reduce to complete generator, but it's not like the most.
Yes, but is there any chance that you would have in this manner actually something, if you start with complete like that you would have some which will turn a short exact sequence with completely generated parts.
Well, I mean, you will get such short sequence, but only after passing to calculate case with origin. Something like this, but I mean not for the origin. Yeah. No, okay. Let me just mention briefly that there is another approach due to Gregson, which represents, for example, K0 of K1 of a category as a direct summand of K0 of another category. Kind of small, which, like in the case of vector spaces, you consider coordinate rows like xy equals 0 and model by GM and consider complexes supported at 0. Translation of yeah, it's I mean, here Grayson explained it kind of in a more complicated way, considering binary complexes like complexes with two differentials, both which are affected, but if you just translate it using Qt structure and just some formal manipulations, you obtain this geometry. But still, it's a direct summand, and then if you just try using this approach, which Castor can misuse, but then they needed to do horrible things like reducing the length of this binary complex to 7 after direct summands, yeah, which is uniformly bounded constantly. But it's okay, they didn't use any dualizable cases, but from my point of view, like okay, here we have this complexity with limits and colimits, but from my point of view, it's just much more conceptual way proving this. Anyway, as you see, there is no completely elementary proof. Yeah. Okay, so now let me at least formulate 3 different approaches which give the same result for the case associated with Bornholm scheme. Yeah, okay, so formal schemes, let's just consider affine noetherian formal schemes. So are I is ideal. So I will give 3 equivalent definitions, but actually, like the fact that the result is well behaved involves some quite non-trivial, quite non-trivial assertions about this limits, dualizable limits, and other constructions. So, like first definition, so 3 equivalent definitions of the same category. First definition is that nuclear category, to be more precise, this is slightly different from the original version of the nuclear category constructed by Clausen and Scholze. So let's just note that nuclear filter, so let's emphasize that it's slightly different category. So this is the dualizable.
It's category difference, not definition difference, but the category is
the category is slightly different. Yeah.
So you will can you reveal the secret what was the notation? So you will give 3 very different finds 3 very different categories and which turn now. Yes.
Yes.
The previous, what's the notation?
I will use the same.
We use the same notation because
Yeah, but the equivalence is not immediately obvious. Yeah, but we'll see. Yeah. But probably tomorrow or just on the next talk, whether it will be tomorrow or Monday, we'll see in more detail what happens. So the third definition is I'm just taking sequential inverse limits of the usual derived categories of R of I to the negative. Yeah, so as I mentioned, as all limits exist, in particular, I have a right to take this limit. Second definition, following. Let's say category. This is the internal home, but taken in the category of dualizable categories. So the category of dualizable categories is still symmetric monoidal with the Lorentz product. So I'm taking the internal home from this derived category, which is locally Itosh homology. Locally Itosh, or equivalently, you can take derived I-complete R modulus, equivalent category. So I'm taking the level internal home from this to the derived category of R. Yeah, sorry, and I'm doing this relative over R. So this is internal home in R linear dualizable categories. Yeah, I didn't quite explain this, but existence again like follows from general nonsense.
existence of what internal homes.
So
It's the existence
existence of internal homes. Yeah, in general, yeah, from between R. Yeah.
By definition, the dualizable category is the richest function.
Yeah. Yes. Yes.
Functions of the richest.
Yeah.
However, my understanding is that so the danger is that so naively dualizable categories of the chips. But it's true if we consider a special types of present.
Yes. Yes.
Which means that one more distance are but we want that as
Non-full surface.
not as
Yeah. Yeah.
another one distance. So we're saying that it's so probably it's not true that the combinations.
It's certainly not true. No.
Are you saying that they still form a symmetric monolithic?
Yes. Yes. Yes.
But not a rich. Not a rich. However, there exists internal forms.
Yes.
But it's not.
It's not trivial. Yeah. And its complexity is kind of similar to the complexity of the dualizable. And for the third definition, I would first need to recall this concept, which might be familiar some people don't. The concept of a rigid, large rigid symmetric model category. And this notion is due to K-theory and Rosenblum, but I will give the definition which is different, which is kind of more explicit, and which is similar to the definition of dualizable category, which I gave previously using complex model. So first, recall just a very general concept of a trace class map. So let's he closed symmetric monoidal category, like category, I mean infinity category, but it might be also just the usual one category with internal form. Then a map, so a morphism f x to y is trace class if so if you consider this as an element, so if you consider f as an element of y0 of maps from x to y, then it comes from an element of y0 maps from the units to internal form from x to the units tensor y. So there exists some element f tilde which goes to f. So basically, intuitively, it's like having finite rank if we're talking about vector spaces. So yeah, but this node makes sense just in arbitrary closed symmetric monoidal category, not necessarily stable. Yeah. Yeah, and then definition representable symmetric monoidal category. Some tensor product, and here I'm tacitly assume that the tensor product commutes with colimits in each argument. So presentable figure. This category is called rigid, and first of all, the unit is compact. Second, the category is generated by this counter-represented objects, as we had before for dualizable categories. Third is that for any counter-represented object, x is equivalent to a colimit of a sequence y1, y2, so on, where all the guys are one represented, and each map from yn to y plus 1 is trace class. So the intuition that this category kind of looks like incompletion of a usual small rigid category. It's like in the case when the category is completely generated, this simply means that compact objects are the same as dualizable objects. But in fact, with the definition, category doesn't have to be completely generated. There are much more examples of rigid categories.
What was so you are saying that this definition the Rosenblumen category, and what was their motivation? What is
I mean, they kind of deal with categories of geometric origin, and the definition was different from this one. But yeah. Oh, sorry. Forever, yeah. Yes, there exists such an approximation. Yes, so they considered they had a different definition, like which is closer to Lurie's definition of dualizable category, just in terms of existence of the.
so I shouldn't try to find
Yeah, it exists only in talks. Yes. Yeah.
Okay, so anyway, you gave it.
Yeah. And then you can actually observe remark which is just immediately follows from this definition, is that if C is a rigid symmetric monoidal category, then C is dualizable. Yeah, because all trace class maps are compact, and assuming that the unit is compact. Then trace cost maps are correct, and so rigidity implies dualizability. Yeah. And so there is a general result about existence of rigidification, or can be also called a stone check rigidification, despite this universal rigidification. So I will explain in more detail later, but now let's just say that so if you consider all symmetric monoidal presentable stable categories, so we have a functor to rigid categories in this sense, and there is a right adjoint. For verification, right? Or vice versa. Yes. We have functor here, and we have the right. So for any symmetric monoidal category, there's a universal rigid category mapping into it, as I said, by symmetric monoidal functor preserving colimits. And I will explain later how this stone check rectification works, but assuming its existence, the third definition of this nuclear category is so as a symmetric monoidal category, it is defined as a rigidification of the usual I-complete or I-torsion. Let's say I-complete derived category of R. So we take this category and take this rigidification. So from the point of view of formal properties, let's just mention formally that this kind of analogous to locally compact Hausdorff space, which is moreover countable at infinity. And the specification is analogous to stone check specification. Yeah, and so all of this definition can be the same thing. Let me just mention that in this category, it is of course completely generated, and of course all compact objects are dualizable, but the all compact objects are rigid, but the unit is not compact. So I mean, there's no, it's not a stupid thing to write down. So I mean, this category is not rigid. So just because the unit object is not compact. Yeah, so I have the impression that they, I mean, I can continue with more explanation, but I have an impression that people are a little bit tired of this because of limits. But unfortunately,
Because
yes.
to our
But, yeah. No, but I have to say that there will be I will have at least to mention more statements about limits of colimits, because you cannot completely avoid them, because they're very important. I mean, just to be able to say anything about this category, in particular to try to compute this quadratic invariance, you need to actually do some inhuman patients. But I will not go into like full details, but I will at least mention which statements are relevant.
I remember that there was some text. I don't know where.
Any question?
Clarify, so when you work with rigid categories, sorry, so I was wondering what the definition of the category of the category of rigid categories. So the rigid categories work with tensor, just all continuous tensor functions.
Yes, all colimit-preserving threshold on the functors.
So you don't need it, so strong continuity is automatic.
When you make it out of rigid K-theory, then it's right.
That's because
Assuming that the target, the unit is complete.
yeah, I think it would be yeah.
So you gave me options.
Yeah.
And then plane is and another plane is there.
But this was a vague statement, yeah, but I will explain what it means.
And the meaning of the explains.
Yeah, but I mean, okay, like one of the meanings I can explain right now that I mentioned that very abstract that we have this quite abstract situation of those limits in general, but it simplifies considerably when a certain functor is a homologically homomorphic. Because then this dualizable kernel is just a usual kernel. So this is what happens here for quite a non-trivial reasons.
You actually follow this organization of R.
Yeah. Yes. Will be a quotient function. Yeah. Actually, this is the symmetric localization of this language of symmetric monodictation.
What kind of
Symmetric localization. Yeah. Well, smash.
it is I don't know but it's
Yeah, quoted by the kernel.
kernel which is far from being
The usual perfect.
and sadly there was slightly different. Right?
By Clausen and Scholze. Yes.
And they are different, but
Theory actually is the same.
the theory is the same, and it's the character of synthesis, the character of the things.
Yes.
And this is where at least one of them interventions.
Yes.
For instance, the one kind of extension. If you have function. R is standard. Maybe after a direct sum.
No, but actually any object can make it. I mean, we're talking about large categories, so any object.
And
Yeah, but I have a feeling that at least four require want to cover material about the theory of total categories and also material about quantum processes. Also,
Then question. So we need, as you are saying that we need. Yes. And probably it's not.
for me, not, but
So now, now the question is when we have what is the tomorrow we have a room. However, there's a problem.
Open with geometry in 430.
So there's
There's a clue in upgrade geometry until 430.
until 4:30. Okay. And interestingly, it's the same room that I reserved, it's in this room, which I reserved from 3 o'clock for you. They did notify me that, so this is why I say that theoretically it's available, but something is wrong.
maybe some other room.
Okay, so in theory, it's available. And if so, then. What's that is or what?
There is certainty on the room.
Certainty when.
Well, again, for me, it's
Are there any objections? So in uncertainty, I maybe, I don't know, maybe it's the department of uncertainty.
I think the visitors are not allowed if someone else doesn't let them. It's,
So it's okay. So are there more serious objections?
Sorry, I think the room is available, so I think we emailed about this, I mean, for the colloquium, I'm responsible for the colloquium.
Yeah, you're
We
responsible.
emailed about it, but I think we emailed about it a few weeks ago, that because the colloquium was canceled, I might say, but I think it is free after the colloquium, so we could start here after the colloquium.
So we could, so your suggestion is to meet here after the
And we can start at like 4:40.
but for 4:30 is too, so for 4:40.
4:40, yeah, basically, after.
Okay, so then we meet tomorrow in this room at 4:30. Okay.
And probably there will be a talk on Monday as well.
and yeah, I mean, we can make it on Monday or maybe sometime later. Yeah, I don't know.
Okay. So anyway, we meet probably, yes, we can meet on Monday. Just a moment, yes, Monday. Sorry, sir, so Monday is a regular day, theoretical day for the seminar. There is a room at 4:30, but it's not this room, it's Ryerson 358. It's probably it's big enough. Plus, and if you work out tomorrow, that should be.
Yes.
Then we borrow here, there's four. Other scientific question. Let's just take this